Yeah, okay, so good morning. Um Today's lecture basically will be a very, very long one, and also I forgot to update the topic. So I just tried to include the third topic to this, like the types of reaction part. So we also have part of types of reaction here too, and types of reaction. So it's really a long class, so we just have to be fast with it, and so we won't be bored before the end of the class. But basically, they are all interesting topics. Like these topics are the core of chemistry, and if you know these topics, you can boast a little bit that you know chemistry. That's the idea. So, not to waste much time, let's shoot. So, starting with these, like this particular slide is very, very interesting. Like, okay, I try to also um be playful with it. So okay, let's get the main ideas we need to get on stoichiometry. You know what stoichiometry is? It's one major topic in chemistry. It may be a lot. Sorry for that sound. Like it may be a lot, but I feel it's something we can just deal with and be done with as soon as possible. So the amount of each reactant present at the start of reaction determines how much products can be formed. That means your reactant determines the product. In case of two or more reactants or products, the amount of a reactant or product reacting or produced, as the case may be, also depends on the amount of other one used. Let's say, for example, you have A plus B giving me C plus D. A will depend on B, and also C will also now kind of depend on D. That's the idea. Or let me just say C and D depends on A and B. That's the idea there. So molar mass is the mass of one mole of a substance. Very important that you know that, oh, 1 mole of sodium is 23 grams. That's why 23 grams is the molar mass, the mass of 1 mole. The same thing with molar volume, which is what? Volume of 1 mole at STP. That's the idea there. So from the two ideas above, yeah, we can say volume of a gas and mass are equivalent to the molar mass. Okay, from the ideas above, we can say that the volume of a gas of mass equivalent to molar mass is the molar volume. Yes, that may be somehow because okay, I said the molar volume is the volume of 1 mole of a gas, Abina, and molar mass is the mass of 1 mole. So that's I'm not saying okay, the volume of a mass that is the molar mass is the molar volume. That means the volume of a mass that is molar mass. In the case of CO2 now, molar mass of CO2 is 44 grams per mole. The volume of 44 grams of CO2 is the molar volume of CO2 too, because 44 grams of CO2 means 1 mole of CO2. That's the idea. Okay, so what is stoichiometry now? So they won't ask you this, but let's just know what it is. So basically, it is derived from two Greek words, stoichion and metry, which means what? Atom and measurement. Stoichion means it's relating to atom, composition of atoms. Then metry, which means measurement. That means you're kind of measuring atoms in a chemical reaction, in a compound, everything. That's the idea. So it can also be regarded to as a study of quantitative relationship between the amount of reactants used and the amount of products formed by a chemical reaction. This is called stoichiometry of a reaction. Okay. So and it is based on what law of conservation of mass. Very important. Okay, moving on. So from the previous slide now, is it that like we are saying it is kind of based on what conservation of mass, and that actually means that the mass of the reactant must be equal to what mass of the product. This means we must always balance our reaction. Okay, from what we have above, 73 grams, okay, 100 grams of calco 3 reacts to 73 grams of HCl. That's what 173 grams in total. Then the product side, we have 111 grams of calcium chloride, 44 grams of CO2. I'm using their molar masses. Then 18 grams of H2O, making how many grams in total? 173. 173 must be equal to 173. That is its conservation of mass. So 1 mole relationship. So to get your stoichiometry better, I always enjoy using this method. I always enjoy using this method a lot. So it is the idea of 1 mole. Like you have to know what 1 mole is. So 1 mole of a substance is the amount of the substance that contains exactly 6.023 times 10 to the power 23 particles. This can be atoms, molecules, or ions. That means 6.02 times 10 to the power 23 particles, 6.02 times 10 to the power 23 atoms. It can be in any form, or even electrons, as in electrolysis, where power this constant comes in. So that's the idea. So 1 mole of a substance can be used, can also be defined to that which have the same amount of particles as 12 grams of carbon 12. Yeah, you may not get that now, but let's just keep moving on. So 1 mole of a substance is the basis of stoichiometry. That's just the idea. 1 mole of a substance is kind of what stoichiometry builds on. So when you understand what is in 1 mole of a substance, then you understand everything. Okay, moving on. There's a lot of slides, like a lot. So, but we just have to keep moving. So 1 mole to molar mass is a relationship now, although I've explained this before. So I said what molar mass is the mass of 1 mole of a substance. Molar mass is the mass of 1 mole of a substance. And if we say the mass of CO2 is 44, if you have 44 grams of CO2, that means 44 grams is the molar mass of CO2. If you have calco now, which is 100 grams per mole. In fact, the unit of molar mass is what 100 grams per mole, which means mass of what 1 mole. That's the idea. So if you now say 2 moles of calco will be what 200 grams. If you say 5 grams of calco you say what 500 grams. If you say 2 grams of CO2, you say 44 grams. That's the idea. So mole to molar mass. So what the idea is, to get it better, just sit yourself down and then give yourself some compounds and then try to get their molar masses. I don't and their mass is like the mole to mass ratio. Just okay, ask yourself 2.5 moles of CO2 will be what? You know, I already know is what 88 plus 22, which is kind of one thing. So that's the idea. So moving on, just brainstorm on that and then you are good. Moving on. Say formal relationship to mole and molar mass. So the idea is I don't like using formulas. I don't like it. But the point is, if you need it, if you know you work better with formulas, you can just say I want equals to what mass over molar mass. That works. But using formulas at times might even draw you down, but like slow you down rather. But let's just keep moving. So the formula. Let's look at how we can use the formula. What is the mass of 4 moles of oxygen molecule? Whereas, okay, uh-huh. Okay. So, I was just trying to explain oxygen molecule there. That okay, oxygen molecule is what the atomic. I didn't. If I say oxygen molecule is the same as oxygen gas because it is a gas at room temperature. So I used the formula and I got it. So that's just the idea. So the amount is what I'm looking. Okay, I'm looking for the mass. So you gave me 4 moles, and then I know that 32 grams. But in my mind, I know that if 1 mole of oxygen is 32 grams, 4 mole will be 32 times 4. Without even the formula, you're good. Okay, moving on. Then mole to molar volume now. We are done with mole to molar mass. The mole to molar volume is basically a plate. You just work with it basically. But this one is just that it is only applied to gases. Gases are the ones we are using here. In fact, we call it the gas molecular volume. Gas molecular volume in the sense that is the molecular volume of gases at STP, standard temperature and pressure, and the value is what 20.4 gm3. Let's note that. So then 1 mole of any gas at STP will occupy what? 20.4 dm3. Any gas. So you get this one is not like molar mass that the value changes, but yeah, 1 mole of any gas is 20.4 dm3. 1 mole of N2, O2, N2, any gas at STP is what? Don't forget at STP is very important, 20.4 dm3. So that means I can say mass of 1 mole of CO2 is 44 grams, volume of 1 mole of CO2 at STP is what? 20.4 dm3. And I can calculate what? You can calculate the density mass over volume. That's basically simple. So moving on, conversions of volume. Okay, I'm just trying to work with 1 dm cube is 1000 cm cube, 1 dm cube is 1 liter, then 1 dm cube is 1000 milliliter. Let's note that. So formula relationship to mole and molar volume. Okay, yeah, it's just like the mole to molar mass T. So amount equals to what? In mass, you said mass over molar mass. Here it is what? Volume over molar volume. Okay, I used this to solve a question. So I said, what is the volume of 3 moles of CO2? So I'm looking for volume. You give me moles, then the molar volume is what? 0.4 gm cube. Very simple. Okay. molar mass to molar volume relationship. So I said it shortly, like, okay, we saw mole to mass relationship, mole to molar volume relationship. We can also have what molar mass to molar volume. Just like when I say A equals to B, B equals to C, then B is equals to B. That's the idea. So X equals to Y, X equals to Z, then Y equals to Z. Simple stuff. So you also know zero to love thermodynamics. That's the idea they use. Okay, so the idea is that, okay, let me just quickly use this. If I say um 1 mole of CO2 is 44 grams, and I also say 1 mole of CO2 at STP is 22.4 gm cube, that means 44 grams of CO2 will occupy what? 20.4 gm cube. That's the idea. Okay, moving on. So that's just the idea behind this. So if I say don't forget it's for gases when you're doing this too. So if I say um 32 grams of oxygen gas, and then it will be how many, what would be the volume at STP? um Volume of 1 mole of oxygen is 20.4, and mass of 1 mole of oxygen is 32. That means 32 grams of oxygen will occupy what? 22.4 gm cube. Simple stuff. So, and all those things, if 32 grams will occupy 20.4, then you can now say 16 will occupy what? 11.2. You can say 8 will occupy what? 5.6. That's just the idea. So molar mass to molar volume in action. Okay, let's just release. So what volume will 14 grams of N2 occupy at STP? I know that N2 is 28. 1 mole of N2 is 28 grams. So this is half of it. That means the volume will also be half, which will be 11.2. What mass will oxygen molecule occupy? What mass of oxygen molecule will occupy 5.6 dm cube at STP? That's like divided by 4. So divide the molar mass of oxygen 2 by 4. Simple stuff. Not to waste much time, I think I explained. You can just pause and read it. So moving on. So 1 mole to Avogadro's constant. So this one is also very, very important. Just know that 1 mole of a substance will occupy what? 6.02 times 10 power 23 what? Part number of particles. It can be atoms. So 1 mole of an atom will occupy this, of a molecule, of an ion, of an electron, anything. So that's the idea. So um so 1 mole of a substance will occupy 6.2 times 10 power 23 particles. Then 1 mole of oxygen will contain this. So 1 mole of oxygen will contain 2 oxygen atoms. Is there? Who is you? I'm busy. I'm busy. Later, please. No, 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 no. Okay, I'm so sorry for that, guys. Um, 1 mole of oxygen molecule will contain 2 oxygen atoms, and each will contain these particles. That means 1 mole of oxygen will contain 6.0 times 10 power 23 molecules. Let me take this again. When I said 1 mole of oxygen will contain 6.0 times 10 power 23 particles, that's cool. But that's for oxygen atom. She get. So in atom, we can have what? Number of particles in the atom. But when you're not talking about molecules too, for example, now, okay, let's say 1 mole of oxygen molecule will contain how many atoms now? It will be 2 times 6.0 times 10 to the 23, because in oxygen molecule we have 2 atoms. Do you get my point? So that's the idea there. And then 1 molecule of H2SO4 has 7 atoms. So it's now what? Each atom will contain 6.0 times 10 to the 23 particles. Do you get it? That's just that. So, but let's move on. So okay, let's look at some questions. The number of molecules present in 0.1 moles of CaO. Since we are looking for molecules and this is just one molecule, so it will just be 0.1 times 6 power 0.1 times 6.02 times 6 power 20 what? Times 6 power 23. That's the idea on that. One number of atoms present in 1 mole of H2. So in 1 mole of H2 we have 2 atoms normally. So you now multiply it by 6.02 times 6 power 23 again to get the number of individual atoms. So number of ions present in 2 moles of H plus, still the same logic. Moving on. So relating Avogadro's constant to molar mass and molar volume. So this one now, we are relating the three things we've done. Talking about mole and Avogadro's number. So you can say 16 grams of oxygen will contain how many atoms? Shall you get? So it's just like 16 grams of oxygen normally is 1 atom. So it is now what? It's going to be 6.02 times 6 by 23. So 1 mole of CaO will contain the same amount of molecule as 56 grams of CaO. That's normal, right? Because 1 mole is also what, 56 grams for CaO. And that means 56 grams of CaO will now contain 6.096 molecules here too, not atoms. If it is atom, you have to multiply it by 2 because there are 2 atoms in CaO. Moving on. So far, this constants to 1 mole. This is just like a bonus discussion, but not to waste our time much. So just go through it. This is on electrolysis. When we are doing electrolysis, we are going to take it again. So we'll just go through it. It's just talking about the moles of electron discharged. We are transferring rather. The moles of electron transferred. If it is 2 moles, it's going to be um 2 Faradays. If it is 3 moles, it will be 3 Faradays, and that's just it. And 1 Faraday is 96500 coulombs. And coulomb is the what unit for charge. Okay. So far this constant to 1 mole is still bonus. So let's not waste time on that. So stoichiometry of reactions now. So all those ones we've been doing, we are just considering compounds and all. Let's look at what chemical reactions. So not to waste much time, so that okay, let's just move on. Let's move on. Okay, so now that we get the basic understanding of mole to molar mass, mole to molar volume, molar mass to molar volume, and Avogadro's constant relationship, let's see what we now have with what chemical equations. But don't forget, I said it maintains the law of conservation of mass. That means we have to balance our what chemical equation. So let's first deal with balancing chemical equation. So I think we've done this basically in one of our tutorials. So I just had to add it to remind you guys of what is going on. So more of this, I think I explicitly typed it out. Sure you get. So you can just make sure you read everything throughout. So let's look at this now. CO2 plus O2 to give me CO2. I'm coming, sorry for those notifications. So yeah, CO2 plus O2 to give me CO2. How do I balance it? I ended up having what? 2CO plus O2 to give me 2CO2. Now, one thing to note when balancing the chemical equation is that you don't change the substrate. You only change the coefficient. That's the idea. Please don't ever, if, for example, now the O2 in O2 there, you don't change it. But you can have 2O2, 3O2. In fact, you can even have half O2. Depends on you. Okay. So relating the modes of reactants now, so it is getting interesting here. So if you can relate modes, you can relate mass, you can relate volume. But the idea is we are relating modes. So the idea is when you balance your chemical equation, you can do a lot with it. Okay, so we thought we have the air now. What we have here, we thought we have here now. So basically, it is not. Sorry guys, I'm having hiccups. So what we have here now, it is not a quantum mechanics. It's not something so high that you can understand. No, no, no. It's something basic. So let's just quickly go through it. So you have this reaction: 2HCl plus calcium hydroxide to give me calcium chloride plus 2H2O. This is what we are. This is what we are working with. So inspecting the reaction above. In this section, we are only concerned with reactants. So we are going to deal with the reactant firstly. So 2 moles of HCl is reacting with just 1 mole of COH2, calcium hydroxide. That's the idea. That means 3 moles of HCl, we need 1.5 moles of calcium hydroxide. 10 moles of HCl, we need 5 moles of calcium hydroxide. That's it. We are relating moles here. And that's just the idea here. So 4 moles of HCl, we need 2 moles of calcium hydroxide. 100 moles of HCl, we use was 50 moles of. That's just the idea. Very simple. But if I have 100 moles of HCl, and I'm going to need 50 moles of calcium hydroxide, and they gave me 70 moles. That means I know calcium hydroxide is in excess. By how many moles? 20 moles. That's the idea behind those um, excess reagent, but we are still going to talk about that. Just know that 2 moles in this equation now, because of the reactant, because this guy, um, 2HCl is what? It's need HCl is in the ratio of HCl to calcium hydroxide is 2:1. In some reactions, it can be 3:1, it can be 3:2, it can be anything. Moving on. Relating the moles of reactants to the chemical reaction now. So 2CO plus O2 is giving me 2CO2. So I think it is still simple. Using the modes of reactant. This is still like what we did the other time, sha. So 2 moles of CO is needing 1 mole of OT. 3 moles of CO we need what, half mole or 1.5 moles of what, OT. That's the idea. So what if you are now asked the mole of CO that is needed to react completely with 4.5 moles of O2? That would be what, 9 moles, because I need to be times 2 of it. Simple stuff. Okay, make sure you are reading everything because I'm just explaining it. You get read. I tried as much as possible to make it so explanatory that if you don't get any point, you can just pause, read it again, again, and again. You get it. So let's use same reactions as used for the above slides. Okay, we have this dihydrochloric acid plus calcium hydroxide. We are relating the modes of product now, product side. So it is still the same thing. That means after the reaction between hydrochloric acid and calcium hydroxide, you must always form what? 1 mole of calcium chloride and 2 moles of what? Water. That's the idea. So just like the way we related reactant, the same thing applies to what? The product side too. Okay, now relating modes on that of product. So I'm now taking the reactant and product now. So it is also simple. One thing about stoichiometry is that you only deal with what you need after balancing your equation. For example, now let's say for example they say one mass or 1 mole of CO2 is produced from 3 moles of CO in the reaction, in this reaction, or in the reaction between CO and O2. In this case, we don't need O2, you just work with what you need. And you know that 2 moles of CO will produce 2 moles of CO2 when it is reacting with what, O2. That's it. So you can always work with it. You can say 2 moles of CO is giving me 2 moles of CO2. That means CO is going to be 12 plus 16, that's 28 too. That means 28 grams. 28 grams is for 1 mole, right? Yeah, that means 28 grams of CO will give me what? 44 grams of CO2, because 44 grams is also 1 mole. One will give me one, two will give me two, three will give me three. That's the idea there. Moving on. So relating mass and volumes of a reaction for both reactant and product. So we're not dealing with what? Mass and volume now. So using a different reaction this time. Mg plus HCl now to give me MgCl2 plus H2. It is balanced with 2 in front of HCl. So from the reaction above you can see is that 1 mole of magnesium will react with 2 moles of HCl to give 1 mole of magnesium chloride and 1 mole of H2. Okay, I think that's making sense, right? We can say that okay, 1 mole of magnesium is reacting with 2 moles of what? HCl to give me 1 mole of magnesium chloride and 1 mole of H2. That's that. And we can say 1 mole of magnesium is giving me 1 mole of H2. You can just pick any two out of it and just relate it. That's the idea. That's why formula is, you notice I'm not using formula. Formula is brutal. I don't like it. It will just waste our time. So I can also say 24 grams of magnesium, because 24 grams is 1 mole of magnesium. Will be giving me what? 2 grams of H2, because 1 mole of H2 is also what? 2 grams. That's the idea. I said 1 mole is giving me 1 mole. 1 mole of magnesium, 1 mole of H2. But I can also say 24 grams of magnesium, 2 grams of H2. That's the idea. You can do the same to volume. You can even now say 24 grams of magnesium. So it is now H2 gas at STP. And if it is 1 mole to what? 22.4 dm cube. That means 24 grams of magnesium will give me what? 22.4 dm cube of what? H2. And you can relate it. That's the idea. You can always work it out separately too. Okay. So concentration in stoichiometry reaction. So let's see what the concentration is. Concentration basically, I think I defined it. Okay, yeah. I defined that the amount of a solid that can be contained in 1 dm of a solvent at that particular temperature. Okay, that's the idea. Okay, this I'm referring to a PDF here actually, because I also that's the one we did, but it should be the video you get. So the video we had on solubility. I said I think I defined solubility as what, the amount of solute contained in what, 1 dm cube of what, solvent at a particular temperature. Temperature very important for that. I think I explained that quite well. Then concentration is similar. This is also the amount in mass or mole. That's it, molar concentration or molar mass, as the case may be. That can be in 1 dm cube of what, of its solution. That's the idea. But in solubility, it must dissolve. Here, it is just in it. So if I pour 10 congos of sugar inside 1 congo of water, it is just very concentrated, and it will be 10 Congo per 1 Congo of 10 Congo of sugar per 1 Congo of water. That's the concentration. I'm concerned with the one that is in it, not that the one that is dissolved. But in solubility, it must dissolve. That means you can say solubility is concentration, while concentration is not solubility. Or will not most of the time be solubility. That's that for that. So if I have 0.5 mole per gm cube of NaOH, that means 0.5 moles of NaOH is in 1 gm cube. That's the meaning. So concentration, molar concentration now, we have a formula for it. N equals to CV. That's the mole is equals amount in mole is equals to concentration times volume. A very simple case. So what is the concentration of 2 moles of HCl that will be contained in 4 gm cube of a solution? So 2 N equals to CV, that will be what 2 divided by 4, which is what 0.5 molar or mole per gm cube. Okay. Still on this here, let's assume the value for concentration of 0.2 mole per gm cube, which can also be used as 0.2 molar. It can be reduced as 0.2 moles of NaOH is in 1 gm cube of solution. That's that for that. That means 0.4 moles will be in 2 gm cube and 0.6 moles will be in 3 gm cube, depending on what you are asked. So limiting and excess reagents in a chemical reaction. I mentioned something about that in the previous slide. So I said you will notice that um, I've been using the word excess in some cases. For example, when we started the reaction part, I said maybe 1 mole of CO2 reacts with excess oxygen. Yes, excess oxygen means you have oxygen as much as possible. But don't forget, when you, let's say for example, you have a reaction between CO and oxygen to give us CO2. When you finish using up your CO like this, the remaining oxygen will be useless. It will be excess. While the CO that has been used up is now the limiting reagent. That's the idea there. So using this reaction at Mg plus 2HCl to give me MgCl2 plus H2. So Mg plus 2HCl basically is just they are the reactant trigger. That's where you get your excess and limiting reagent. So let's now say we know that from here 1 mole of magnesium will react to 2 moles of HCl. That means if they now say 2 moles of magnesium is reacting with 2 moles of HCl, we know that magnesium is in excess because we only need the 1 moles of it. So that's just the idea here. So let's take this better. So assuming I was given 2 moles of magnesium, okay, this is what I just explained. So 2 moles, of course, 2 moles of magnesium will need 4 moles of HCl. Then you can now even now say 1 mole of magnesium will need 2 moles of what? HCl. Now I've used up my HCl, but I still have magnesium left. So the one that is left over is what? Excess reagent. The one that I use up is the one that limits the other one. That's what they call it, what? The limiting reagent. Okay, so let's have another equation. From the equation above, I just need 1 mole of O2 to react with 2 moles of C. Oh, not CO2. I'm very sorry for that. I think I need to correct that. So immediately, limiting an excess reagent. Okay, yeah, yeah. So, I need just 1 mole of O2 to react with 2 moles of CO. Anything giving me more than with 2 moles of CO. That's okay. I'm not using the product here. So anything they give me that is more than what I have here is wrong. So if they say 2 moles of CO and 2 moles of O2, that means O2 is in excess by what? 1 mole. Sure you get. So you don't use the excess reagent in your calculation. Yes, most of the time if they give you the value for the two, try to get the one that is in excess and you don't use it in your calculation because you did not finish using it. And if you're not using it to calculate something, it will be wrong. That's the idea. Okay, so moving on. So limiting an excess reagent in a chemical reaction now. So I think how many grams of hydrogen gas will be liberated from 6 grams of magnesium ribbons dissolved in 500 cm of 6 molar HCl. In this case now, just get the moles of these two guys. 6 grams of magnesium. Don't forget, 1 mole of magnesium is 24 grams. So 6 grams will be what? That's for I divided by 4. That's 1 over 4 2. That's 0.25 moles. Then 0.25 moles is now reacting with 500 cm of 6 molar. To get the mole, N equals to CV. That will be 3. So I'm now having 0.25 moles reacting with 3 moles. Definitely HCl is in excess because I only need 2 moles. In fact, for 0.25 moles, I will need 0.5 moles of HCl. But I now have 3 moles. That's a lot. So that's just the idea. Use that here. Make sure you read everything here for proper understanding. Okay. Limiting unnecessary agent in the chemical reaction. Okay, we are still here. It is still basically the same thing. So let's just make sure we get it better. So neutralization reaction. So basically this is something we should have treated in acid and salt, but we still need it here. So one thing I need you guys to get in neutralization reaction is that they are using the concept of N equals to Cv. So for the base, Mb is equals to CbVb. You know what N equals to Cv is, right? Moles equals to concentration times volume. So that's what they use here. So N equals to Cv. So Na equals to CaVa, Mb equals to CbVb. So when you now find the ratio of Na to Mb, you now have Cav over CbVb equals to Na over Nb. That's what the Kava equation. So neutralization reaction is still on this. So I think you have a question. Okay, it's not really a question like that. It is what I've explained. So questions on stoichiometry of neutralization reaction. So we have this. They give us the concentration of sodium hydroxide and then that of sulfuric acid. They did not give us a volume of sodium hydroxide. We are looking for the volume. So from the equation, you can get your Na and Nb. Then use the formula to get your answer. So neutralization reaction, excess reagents. So basically, this one is like a bonus part to share get. So you can just read through. It's very, very basically simple. So okay, let me just quickly do this. So when it's just like the way we are calculating our excess reagent. So when you notice the one that is in excess, so that excess part of it can still be used in another equation, in another reaction for some other stuffs. Share get. So that's just the idea. If you have any questions regarding this part, you can just keep it till when we meet in the night for it. So it is just something we need to interact more on. But it is if you read this, you are going to get it better. It's just that the excess one can also be used in another equation. So you just need to always get the amount of excess you have, and that's it. Okay, moving on. So this thing is getting a whole lot longer. So let's just shoot on with it, and then we are good. So neutralizing reaction, Kava, CBVB, and all. So just equations on that. The dilution principle is just like you are diluting an acid with a base. So when I'm done with the stoichiometry part, I'm going to stop the video then. I will also do the sort analysis part and everything. Okay, so dilution principle is just C1V1 equals C2VT. So going through this, you'll be very, very good. C1 is the initial concentration. You are diluting, and you are making the concentration lower. And you can also remove water to make the concentration higher. So we are adding water to it, and that's just the idea. So that's that on that. Acid and base, yeah, C1V1 equals to C2V2. So when you go through these and you don't have any question, just make sure you reach out. You'll be good on that. So specific gravity and relative density. So on this basically is just a formula. And if you are asked to calculate the concentration from specific gravity, and that's it down here. Molar concentration equals specific gravity times 1000 over what? Molar mass. Basic stuff. So it's just a question on it here, and then you are good. So sort analysis, we are going to treat that in the next video.